In this video, I'm going to be introducing the concept of photoelectron spectroscopy. And it's a technique that scientists use to be able to identify what types of elements are in a certain substance. Since we can't see atoms, we need to find what substances are made out of, and we have this technique where we are sending X-ray light into a substance and getting a feedback. But let's review first. So one of the things that we have talked about are orbital diagrams. And just to relate that orbital diagram, I'm going to draw an image of an atom. We know that we'll go ahead and do the image of boron. This is boron. We know that boron has 5 electrons. So that means that we know that electron number 1 and electron number 2 are housed in the 1s2 orbital. Electron number 3 and electron number 4 are housed in the 2s2 orbital. And then the electron number 5 is housed in the 2p1 orbital. So what we're going to be looking in PES is we're going to be looking at each of these individual electrons and trying to predict what its ionization energy is. So electron number 1, remember we have our positive nucleus over here. Electron number 1 is very close to the nucleus. So it's going to take a lot of energy for this electron to be able to be lost or removed from the atom. Just the same as for electron number 2. Both electron number 1 and 2 will take a lot of energy because they are so close to the nucleus. And in addition to that, remember you have this negative shield which it's being repelled against, so it moves that closer as well. Electron number 4 and electron number 3 are going to again take energy, but not as much as electron number 1 and 2 to be removed. Okay, the one that seems to be the easiest to be removed is the one that's furthest from the positive nucleus, and that will be electron number 5. So what we're going to be doing is we're going to be looking at an image that shows, that reflects what the electron and ionization energy is. So let's look at our first PES, or photoelectric spectrum. What you're going to see is a graph that has peaks, but more importantly, let's look at these axes. Here it tells you the relative number of electrons this atom has, and here is binding energy. Binding energy is the energy or the attraction between the positive nucleus and the electrons. So you'll notice that these electrons right over here have a higher number, which means they have a stronger attraction or more binding to that positive nucleus. These electrons over here have a lower number and therefore have less attraction or less binding energy. So this is an example of a PES for one element, and we're going to determine what that element is. So let's start off by taking a look at how many electrons we have on our first peak. So it looks like we have 2 electrons over here because of those 2 peaks. And on this side over here, and they have a high ionization energy. So let's draw what that actually reflects. So that reflects 2 electrons in a shell that have a strong attraction to the nucleus. And we can only imagine that that must be our 1s shell. Okay, and that's what you see right over here. Now, for the next set of electrons, again, we have 2 electrons, and that must represent in our diagram another S shell, but we see that it has a much less binding energy, which means it must be further away from that positive nucleus, and in addition to that, you have that electron shielding. So we have 2 electrons there, which could easily represent our diagram this way. So this must represent our 2s orbitals. So this would be where electron number 3 and 4 were seen, right over here. Okay, right next to that, not a huge distance away, we have what looks like another peak, and this peak happens to have 1, 2, 3, 4, 5, 6 electrons, and it seems to have almost the same binding energy as the other numbers 3 and 4, and remember 3 and 4 were our 2s2. So it would make sense that this here must be our 2p with its 6 electrons. So 2p6. We don't see any more peaks over here. So there's our 3p. So then I ask myself, what element is 1s2, 2s2, 2p6? Well, if I had these as my choices, and looking at the periodic table, I would say that it is neon that is our answer. Okay? So let's try another one. Here we have, again, multiple peaks. We have relative number and binding energy. You notice that this number is much larger on this end than this number, which is 10. Again, we have a relative number of electrons. It looks like I have 1 and 2 here. So you ask yourself, what would that represent? And we know that these electrons are very tightly bound or attracted to that nucleus. And so we would assume that these would again be our 1s. So let's take a look at which ones you predict these are going to be. So having said that, this looks like it is our 1s2 region. Then we have a big space in between that shows that the binding energy for the next 2 electrons is significantly different, and that would indicate that they must be in a different shell. So I'm going to assume that this must be my 2s2. Then I have electron 5, 6, 7, 8, 9, 10, that's 6 electrons, being in a shell that's in a binding energy that's relatively close to this peak here, but just slightly different. So this must be my 2p6. And then here again, it looks like I have a large space that they have a much lower binding energy. That means it's much easier to remove them. These must be my third shell, being 3, 2s. I have electron number 11 and 12, and lastly electron number 13 in the last peak, 3p1. And that will allow you to identify what that electron is.